Okay, so hi everyone. Sorry about the interruptions earlier. So this is all about the Barbier reaction. You might be familiar with the Grignard reaction, um, which you've already covered in lecture. This is very similar to the Grignard reaction with a few distinct differences. So in the Grignard, there are two steps. The first step is the reaction of an alkyl halide with magnesium metal to form a Grignard reagent. Now remember that magnesium is in group 2. So it has a 2 plus charge when it's ionized. The second step is the Grignard reagent reacts with a carbonyl compound followed by an acidic workup to yield an alcohol. So when you react it with formaldehyde, you get a primary alcohol. When you react it with an aldehyde, you get a secondary alcohol. And when you react it with a ketone, you get a tertiary alcohol. So this is how it works. You normally see the Grignard reagent as that R MgBr. So we have electronegativity above the R group here, and electropositivity around the magnesium. So that gives it that gives the R a somewhat nucleophilic character, while the magnesium gets an electrophilic character. So again, electrons always flow from source to sink, so we have more electrons here. And if you remember back to the NMR lecture, we have not a lot of electrons at this carbon here. So source to sink. And we're going to get that double bond popping up. And sorry about my annotations, I'm doing this with my mouse. So what we see here, I don't know if your professors put any particular emphasis on this, but this is called the tertiary, not the tertiary the tetrahedral intermediate. So this is the tetrahedral intermediate. I'm not going to try to draw that with my mouse. That won't work. So the tetrahedral intermediate is the way you can look at it and figure out how it's going to collapse back down to form your product. So in the Grignard reaction, we normally use polar aprotic solvents because they help stabilize the positive charge on the magnesium. Partial positive, my bad. And you don't quench the reagent. So if you remember back, anything that has a hydrogen will immediately go to the O- we form and form an alcohol. Whether or not it's the O- is even formed yet, anything that is even remotely negative, it's going to go and try to deprotonate. So yeah, any kind of acidic solvent would protonate the Grignard reagent, as its conjugate acid would be a hydrocarbon that has a pKa of approximately 50. 50 is super basic. If we remember, strong acids like sulfuric and nitric acid have negative pKa's. So this is very basic. We don't need our acid to be anywhere near the acidic level to get it protonated. So water would also protonate the Grignard reagent. So reactions have to be done under very dry conditions. What this means is that we have to use THF or ether. THF is tetrahydrofuran. It's another cyclic ether, but it's 5-membered. Or you could just use normal ether. Usually when it just says ether, they're referring to diethyl ether. So both of these are anhydrous. They don't contain any water whatsoever. But the thing is, they're very expensive. Another problem is that to keep things anhydrous and free of all water, we have to use a lot of energy and equipment to maintain a stable environment. So we have to use desiccators and dehumidifiers, except industrial grade and massive and energy consuming. There's also another issue. So these are multi-step two-pot syntheses, which means that you're transferring the reaction contents from one to the other. So that means we increase our chemical waste generated and increase our chemical exposure. And because you're transferring a product is always going to get left behind. And since we're transferring product from one reaction vessel to another, we're going to leave some of that behind, and that's going to negatively affect our yield. Another issue is that solid magnesium metal forms a coating of magnesium oxide, so it oxidizes very readily with the air, and so you have to constantly pulverize it by mortar and pestle so it can stay reactive. So keep this in mind because we're going to bring it up in a second. In Bio 1, we learned about the association between surface area to volume ratio, and that when things get smaller, the surface area to volume ratio gets larger. So when we have strips of magnesium metal, that is a very low surface area to volume ratio. We want to increase that to get better reactivity. Here's where things are different in the Barbier reaction. It's French, so you don't pronounce the R. Okay, so it's stable in ambient and aqueous conditions. It's a one-pot synthesis, so you're not going to be using multiple round-bottom flasks. You aren't going to be pulverizing magnesium at all because it uses powdered zinc. Powdered zinc is going to have a much higher surface area to volume ratio because it's so small. So part of the post-lab assignment is to propose a reasonable mechanism. There's a couple approaches to this, but I think I'm just going to show you one. Whatever the mechanism you do, it needs to make sense with valence electrons. It has to make chemical sense. So it is a free radical mechanism, which I'm just going to show you the free radical part. Alrighty. So we start off with aloe bromide. And zinc. So zinc is one of the only metals that forms a non-variable charge when it's ionized. So it's always going to form a 2+ charge. And if you remember, a covalent bond is just the sharing of 2 electrons, like that. So how do we turn this and get it to be ZnBr? Well, we're going to use some fishhook arrows and we're going to cleave this bond. Like that. So 1 electron is going to the Br and 1 electron is going to go to the carbon. So now we have and so that's just a free radical electron. and I'm drawing all of the valence electrons. And now that we have a free radical on the bromine, bam, we're back to bromine's ground state. Okay. And Zn again. Okay. And now more single arrow fishhook arrows. And now those are attached. Then we get that. We get our Barbier reagent out of allyl bromide and zinc. Okay, so this is for those of you who are coming in person. So rinse with acetone means a very small amount. You're not going to be squeezing the entire bottle into it. Combine the reagents and have the round bottom flask stoppered. I will add the last two reagents. I don't know if I will be adding those or it'll be another situation where we give you a syringe and you add them yourself. Oh, and don't grease the fittings until the reagents are added. We don't want the reagents getting stuck on the grease. Stir for 45. Remember, that goes under the arrow. And now you're going to collect the solution through gravity filtration. Wet the filter paper with ether. So why do we do this? We wet the filter paper beforehand so that when we pour our stuff into it, the filter paper doesn't lift up. And then we're going to rinse the solids with 10 mils of ether when dried. So we're trying to get out all of our organic stuff. And then we're going to cover the funnel with a watch glass. Ether is going to evaporate very quickly. We don't want that to happen. Okay, so reflux condenser. We're working with volatile compounds. Although we're not heating anything, we're still refluxing it. So under the arrow, reflux. We don't put the delta symbol. We don't put the delta symbol there because we're not adding heat. So we are going to be extracting from the aqueous phase with ether twice. That's what it says there. So extracting is using an organic to get out more organic. Then we're going to be drying with magnesium sulfate. This time you are going to be stirring for 10 minutes with the magnesium sulfate. We just want all of the water out. Why is it different this time? Well, this time we're forming an alcohol. So we're expecting something in the IR to show up in the alcohol range. What we want to make sure we're doing is that the alcohol that shows up is because of what we formed and not because of contaminating water. So we want to remove all of the water so we know that we actually got product. And then you're going to concentrate the sample with rotovapping. Obtain a mass, obtain an IR, and bam,